Let's start. Thank you for joining. I hope you can share you can see my screen, and I am audible too. Okay, thanks for joining in. I'm Shashank Jain. I'm working as a senior mechanical engineer here in Decos. I have more than 8 years of experience in medical device domain, and I'm working on structural and thermal analysis of different devices using analytical methods and simulation tools. Let's discuss about the details what we are going to share or discuss today. I have distinctly divided this session into six different topics with why, what, and how of thermal and shock analysis in any product containing electronic components. We are also going to talk about the hand calculations and the process involved in simulating a PCB cooling system. Also, impact or drop analysis. I'll be briefing you about the compliance, standards, and various certifications involved before a product hits the market. Now, let's begin by discussing why thermal and impact analysis have become so critical in today's industrial products. To explain this, I'll walk you through three images which I have captured in this slide and upcoming slides. The first image illustrates how the size of cell phones have evolved over the past 4 decades. Now let's explore the connection between the size of an electronic device and its thermal performance. As device becomes smaller, the space available for cooling component decreases. This limited space poses a significant challenge to increase the risk of, and it also increases the risk of overheating, which can lead to the device failure, especially under high performance or high temperature conditions. Now, over the last 40 years, we have seen a remarkable reduction in the size of electronic devices, especially the cell phones. So if you'll follow the image on the left, you see the Motorola Dynatec, which was used in 1980s, was at a size of 13 inches. It was a brick-shaped mobile phone, a larger one, and it was also heavy in size, heavy in weight. But today, they have been miniaturized into. I'm sorry. But today they have been reduced or miniaturized to a size so that they can remain in by the size of your palm itself. They are more pocket friendly, they are smaller, and even smaller models than the size of your palm has already been developed and manufactured, right? Now, the second image I'm sharing here highlights the growing complexity of electronic components inside our cell phones. It shows how the number of components mounted on a PCB has increased dramatically over the decades. Now, back in 1980s, a typical cell phone had a fewer than 500 components, as you can see at the start of the graph. But today, the number has exploded to more than a million components. Now, this is because the massive increase, and it's important to recognize that most of the components are heat emitters, right? Most of the components which are being included in the cell phone are can be considered as heat sources in terms of thermal terms, right? Also, with each component addition, the weight of the overall assembly also increases, right? And we are aware that the mass is directly proportional to the impact the assembly has to experience when dropped, making it more vulnerable to the shock, right? Now, in we are aware of the, like I already told you, that every component corresponds to a heat emitter or a heat source. So now let's all ponder upon the following question, which I have included in the instruction in the interaction tab. I want all of you to use your due diligence to answer the following question. You will get 30 seconds to answer this question. The question is, what would be the maximum temperature your cell phone can attain working on full load condition in case there is no malfunction in your system or cell phone? You have 30 seconds to answer this question. Try and select the probable value which you think a mobile phone will attain. Take your time. 15 more seconds to go. feel free to record your answer. Another 1 second. Okay, thank you so much. So we have two answers. One is 41 person has chose 45 degrees Celsius, other person chose 55 degrees Celsius. Let's jump on to the right answer. Now, the right answer is to the question is 55 degrees Celsius. The image in this slide shows a graph depicting how the upper limit of the cell phone temperature keeps on rising with more and more inclusions of different technologies. Now, with each new feature which we add to a cell phone, whether it's a fast charging or its advanced AI capabilities, that is artificial intelligence capabilities, which are being integrated with the latest mobile phones, or any advanced graphics, your better gaming experiences, all these things all introduce additional heat sources inside the device. In order to perform a particular activity, you need to increase the number of electronic components within that particular assembly. In this case, it's a cell phone. So while the device size has decreased, the internal heat generation has significantly increased because of the rise in the components which are being integrated into the electronic device. Now, this makes thermal management more challenging than ever. So, the first image shows you how the size reduces, and over here we say that the number of features within the cell phone keeps on increasing with every new model. Okay, so they both go hand in hand. You are decreasing the size, you are increasing the feature. Again, the rise of temperature keeps on increasing with every addition in an electronic component. So that's the challenge which every thermal engineer has to face when he is working on the cooling techniques, right? So we discussed the scenarios which makes thermal and shock analysis an indispensable part of design and development process. Hence, we move on to discuss the next question, that is, what are these analysis all about? The purpose of thermal analysis is to quantify and manage heat dissipated under operational conditions. The focus areas of thermal analysis includes identification of temperature hotspots and evaluation of heat flow. Also, to estimate what would be the cooling solution you're going to use. I have included the objectives which you will achieve by thermal analysis under the head of significance. What is the significance of thermal analysis which we do for any product? So, first, it ensures thermal reliability by preventing overheating, which can degrade materials, components, and solder joints, ensuring system longevity. Then, it improves performance by identifying hotspots and optimizes thermal paths to maintain performance under all operating conditions. It also enables you to take informed decisions on whether you are going to use heat sink, you are going to use a fan, you are going to create a ventilation design, and that too early in your product development. Okay, during the early stage of product development itself you can make these certain decisions, right? Also, it helps you to avoid thermal fatigue failures or evaluate temperature cycles that can cause expansion and contraction, which reduces the risk of fatigue cracks and joint failures. Just want to highlight what is a thermal fatigue. So consider an example: your phone is just kept on a table, and the temperature of the phone will be somewhere near around your room temperature. But as soon as you pick it up, you unlock it, you start using your camera, one app, second app, third app, you go on to use the fourth app. Now, as you keep on piling up these apps, the temperature of the cell phone keeps on increasing because it has to perform more computation in the background. Right. Again, you kill the all the apps. You're done using your phone. You keep it back on the table. It comes back to the room temperature. So there is a cycle which it has to undergo from room temperature to goes a higher value of temperature and then comes down. Now this may happen 100 times or more than 100 times in a day. This introduces thermal fatigues in a electronic component, right? So your thermal analysis helps you to avoid these thermal fatigue failures, right? And lastly, it also helps you to regulate compliance. It assists in meeting thermal safety standards which are defined under different standards like IPC, JTEC standard, or etc., which are also critical for certifications and different market approvals before you enter into a particular market. Now here I'll be discussing about what is shock analysis. The purpose of shock analysis is to evaluate the response of an electronic device to mechanical shock and impact, which a device may experience during operations or during transportation. Okay, during the by in shock analysis, we consider the entire lifespan of the product, like whatever shocks it has to undergo during any of the process, right? Once it is manufactured. Now, this analysis also helps you identifying the stress concentrations, deformation zones, and potential failure points. These also constitute to the focus areas of shock analysis. Now, what is the significance or what are the objectives you achieve when you do the shock analysis? The first one is to which it ensures structural integrity by evaluating the ability of the components to withstand sudden forces. Now, these forces can be in terms of drops, it can be impact, or it can be a transportation shock, it can be any other during the product, entire product life cycle of the product, as I already mentioned. And in the second, like it protects sensitive electronics by identifying failure prone components like ICs, PCBs, and connectors, or any other component which is inside the assembly. Now, these failure-prone components are vulnerable to mechanical shock because if they are left unbalanced, if there is an unbalanced force which applies on this component, that may lead to the failure of a particular component, and then it will affect the overall operations of the assembly or the product. It also improves product durability by enhancing robustness in real-world handling conditions, increasing product lifespan and customer satisfaction. It also helps you in designing packaging for a particular assembly or a product based on what is the design, based on what is the geometry, based on what you are going to safeguard within the electronic component. So it helps in designing shock absorbing packaging and mounts, and it which is crucial for the safe shipping and installation also during the operation, right? It also reduces warranty claims. Now, I say that thermal analysis or shock analysis makes a better product. It ensures structural integrity. It makes it more reliable. It increases the product durability. So overall, when all these things are increased, automatically the product returns and repair cost decreases. You have lesser product returns. You have because you have a better longevity in the product, right? Now, let's move on to discuss an example on how we can estimate the maximum temperature a PCB can attain due to various SMD components. For that, I have included a small case study of hand calculations where I am considering a 1 inch by 1 inch PCB which is mounted by a capacitor, an IC, and a transistor. Now, why we need this and why I have included this case study is because of the significance of hand calculations. When you understand the basics, you are able to estimate based on your subject matter knowledge. You're able to estimate to what extent your PCB may attain the temperature while working during the operation. Correct, and this hand calculations also helps you to compare your simulation results with hand calculations to up to an estimate. I am not saying you will get the exact value in both the cases. The simulation results can be much more elaborate and accurate, but also the hand calculation provides you an estimate to what range you should consider, like what you're going to attain even in the simulations. Okay, so that's why I have also included the hand calculation slide here before we go on to discuss the simulation process and the methods. So the table in the green corresponds to the components, uh, specifications, and the power dissipation values. The capacitor I'm considering is a ceramic SMD capacitor with 100 nanofarad as its capacitance and 10 volts as its voltage value. The power dissipation value is zero point 0.1 watts, which is directly taken from the data sheet. The IC is a BGA microcontroller with a package size of 5 mm by 5 mm, and the power dissipation is directly taken from the datasheet again, which is zero point 0.5 watts. And the transistor is a power switching transistor, and the power dissipation values are calculated using I square R formula, where I is the discharge current and R is the resistance. So it gives you a value of zero point 0.3 watts. So the total power dissipation is zero point 0.9 watts. So what does power dissipation signifies? So it signifies that this is the amount of heat which is generated when the PCB is operational, right? So This is the quantum of heat which you need to take away from the system to ambience or to some other system in order to maintain the temperature of the PCB at whatever is your desired value, right? That's how you are able to decide what should be the cooling method which I need to take up or which I need to circle on in order to what is the quantum of heat which is going out of the or what manner I'm going to take out or out of zero point 0.9 watts. Is it the 100% which I'm going to take out, which is not possible? You can take a quantum out of it. So the effective cooling methods will take you more towards the 100%, right? So that's what total power dissipation signifies. The second value is the PCB thermal property. Now we know that I already said my PCB is of 1 inch by 1 inch and it is a three layer PCB. So obviously it consists of two components. The first component or material constituent I would say is copper. Another one is FR4. So if I'm considering that the total thickness of my PCB is 1.6 mm, then the copper layer, which single copper layer has a thickness of 35 microns. So three copper layers will have a thickness of 105 microns. So how much is 105 microns from this 1.6 mm? That constitutes on in terms of percentage, it comes out to be 6.56%. Right. Based on this, the thermal conductivity of copper, we know raw copper is around 385 to 400 watts per meter Kelvin. So, based on this, we calculate the value of K effectiveness, the percentage of material constituent multiplied by the original thermal conductivity. Similarly, for FR4, which constitutes around 93.44% of the total material, correct? So that the value finally comes out to be 25.56, which you can follow in the blue table over here at the bottom right corner, right? Okay, let's move on to the next slide. Now here, let's discuss the thermal resistance network. Now we already calculated the effective conductivity of the PCB board. We now move on to apply the heat transfer formulas to the overall assembly. I am considering conduction and convection heat loss only. Radiation is not considered in this case study. So any thermal, like the way I'm explaining you the case study, it is very similar to our resistance, which is through which the current passes, and there is a voltage which is maintained across the terminals. Similarly, in this case, there is a heat moving from one end to the other. In between, you have a component, okay, and there is a temperature difference between the two terminals, right? So that's how like we mimic the scenario and we calculate the thermal resistance value. Okay, in any heat transfer can happen only by three modes. The first one is your conduction, the second one is convection, and the third one is radiation. Okay, so here I am considering only conduction and convection. We can consider radiation also, but for the ease of hand calculations and for the ease of understanding, and over here I just want to give you the principle, the way we are going to do it. Okay, in your calculation based on the scenario, you can consider radiation or you can also skip it because I'm considering only three components and a limited amount of heat which I that the total value of heat power dissipation, so that's why I'm not considering radiation over here. So the first mode which I mentioned is conduction. So in case of conduction, for a thin wall without any internal heat generation is given by the formula thickness of the PCB divided by the product of effective thermal conductivity and area of the PCB, right? And for second one is the convection resistance. So what I am considering in my case is the PCB is exposed to natural convection. So when we read about convection, we know there are two types of convection, uh, free convection and forced convection. So in my case, I'm considering a free convection. In free convection, the heat transfer from the PCB surface will happen by the convection currents, natural convection currents. Now, what are these natural convection currents? We all know that on the surface of the PCB. Also, I am considering both the surfaces of the PCB. The air, it will be exposed to the air. Both the surfaces will be exposed to the air. Okay. So in natural convection, when air comes in contact with the air which is closer to the PCB surface gets heated up because of the power dissipation. When it gets heated up, the temperature of the air increases, the density decreases and moves up, right? And when it moves up again, it gets cooled down, the density increases, it comes down. So this creates a convection current. So this naturally air moves from the bottom, takes away the heat from the surface, goes on the top, dissipates it, then comes back, right? So this is what I am considering. In my case also, I am considering it to be a free convection. So the convection resistance is given by 1 divided by the convection coefficient multiplied by the area of convection. Okay. And the total thermal resistance, so as a result we calculate by R conduction plus R convection, which comes out to be 51.8 Kelvin per watt. And in the fourth value, or the fourth step, is the temperature rise calculation. So I already provide you analogy between the electronic circuit and thermal circuit. So based on using that formula, we calculate the value of maximum temperature to be 71.6 degrees Celsius. Now, although I already mentioned the assumptions during my explanation of the hand calculation, I have also consolidated the assumptions at the bottom right corner under the head of key assumptions. Okay, I'll just reiterate the assumptions before we move on to the next slide. The first one, we are considering that the entire PCB surface has a uniformly distributed heat. Originally, in actual case, it may not happen, but because we are using formulas, so there are certain assumptions which comes along with the formula. So the entire surface is have a uniformly distributed heat transfer. Then the second one is natural convection dominates and radiation we are ignoring. I has already mentioned that. Thermal contact resistance are negligible. There is no heat loss when the heat is moving from one component to the one body to the other body. For example, component to PCB. We are considering steady state conditions. We consider the PCB is turned on and then it is kept on for a long time in order to mimic the steady state conditions. Okay. And the fifth one is the perfect thermal contact. Let's move on to the how thermal simulation is done using different tools. Let me take you through the process of simulation tools. What exactly happens? This is, remember that the process I'm showing here is irrespective of any particular simulation tool, but it is just an overview of various steps which are involved in performing thermal simulations. Okay, you can use ANSYS, you can use SolidWorks, you can go for Nastran, you can go for COMSOL, like any tool which you are going to use, but the overall bird's eye view process layout remains same, right? So the steps involved are identifying a significant heat source. Most of the time, even in the hand calculation also, what we do is we go for a 80-20 rule. It's not necessary that you're going to cover all the components in your thermal analysis one by one, but what you do is you try to identify certain components which constitutes to around 80% of the heat which is being generated. The heat generated by that I mean the power dissipated, the summation of the power dissipated comes out to be the 80% of the total heat which is being generated within the system. For the rest 20%, you can ignore that. Right. So that's how that is in the first step, identification of heat sources. And then you import the PCB geometry into simulation tool, and then you define the ambient and environmental conditions. And then we run the analysis and review the results and record the feedback. Now, where the role of an engineer comes into picture is the how you translate the actual conditions like the ambient temperature, the what's the airflow, what is the power dissipation, selection of heat sources, and then you translate everything into a simulation tool. Now in simulation tool, what you are doing is you are trying to mimic the physical world in a virtual world, right? And the translation, how perfect is the translation, will decide how perfect are your results. Simple, right? So in any simulation goes on by like that. Once you get the results, and then you again come back to your original conditions, assumptions, which you have defined in the simulation tool, and then you again reiterate it, and then you again go on to find the exact result which you think is apt for the and should be the simulation results. And in the different results, you can get the temperature distribution, you can get the hot spots where the temperature is high. Then in if it is CFD is involved, then you can, or it is a forced convection, then you can find how the flow of fluid, which can be air, is moving from one end to another. Okay, what should be the position of the fan, is it right or not, you want to change the position of the fan, and so on and so forth. You can make those decisions using the results and using the feedback of the simulation tool. Now, similar to thermal analysis, rock analysis also involves importing geometry, defining ambient conditions, etc. Okay, but what I want to mention over here is what is the basis or the mathematical uh, conditions on which the shock analysis works. So it's the computational method is the explicit dynamics. Now, this computational method is used in finite element analysis to simulate the dynamic behavior of structures and systems, particularly those with high speed impacts, short duration events, and large deformations which may occur into the system. Now, its application includes drop test, impact analysis, penetration analysis, crash simulations, explosions. All these analysis can be done using explicit dynamics, which is a computational method in finite element analysis. Now, before we move on to the next topic, let's take a pause and together we'll watch a video which compiles the various PCB cooling methods.
Printed circuit boards, or PCBs, are the backbone of modern electronics. As devices become more powerful, effective cooling techniques are crucial to maintain performance and reliability. Let's explore some of the most common and advanced methods for cooling PCBs. Conduction cooling is a fundamental technique that involves transferring heat through direct contact. In PCBs, this is achieved by using materials with high thermal conductivity, such as copper or aluminum. These materials efficiently draw heat away from critical components, preventing overheating. Convection cooling utilizes the movement of air or liquid to dissipate heat. In forced air convection, fans or blowers are used to enhance airflow across the PCB surface. This method is widely used due to its simplicity and effectiveness in maintaining optimal temperatures. Liquid cooling is a more advanced technique, ideal for high-performance applications. It involves circulating a coolant through channels or pipes in the PCB. This method provides superior heat dissipation compared to air cooling, making it suitable for demanding environments. Heat pipes and vapor chambers are sophisticated cooling solutions that leverage phase change principles. Heat pipes transfer heat through the evaporation and condensation of a working fluid, while vapor chambers spread heat evenly across the PCB. Both methods offer efficient thermal management. Emerging cooling techniques include the use of thermoelectric coolers and advanced materials like graphene. Thermoelectric coolers use the Peltier effect to create a temperature differential, while graphene's exceptional thermal properties offer promising avenues for future PCB cooling innovations. As technology evolves, so too will these cooling solutions.
Okay. Some of the latest trends which were mentioned in the videos, I have also included in this slide and try to like consolidate all the cooling technologies which are used in electronic devices nowadays, which constitutes to the word latest trends, right? Now, for easy understanding, because they were already mentioned and they were explained in the videos, like name them. This is what you can use. This is the one which is recently nowadays it is being used. So for easy understanding of these technologies, I just categorized them under two heads based on the assimilation of the information which is captured in this slide, right? Based on the different techniques which are mentioned in this slide. Now, the first one is the advancement of heat removing materials, right? The more advanced or better is the fluid which is coming in contact with the heating surface, the better is the heat absorption capacity of that particular fluid, the better is the amount of heat, or the better is the medium of the better is the fluid which can take away the heat from the system. So the more heat it can absorb, better it is, correct? Now, the different techniques which involve or which use only this particular criteria of advancement of heat removing materials, like there some of the methods which are also mentioned here are advanced thermal interface materials, hexagon boron nitride, graphene based cooling, phase change materials, and etc. Now, just want to touch base upon phase change materials because there are two constituents of heat which is which on which this phase change material works. The regular fluids, they are going to come in contact with the heating surface, they are going to get heat up, and then they are going to move away from the system, either naturally or by forced methods. But in phase change materials, what happens is once it comes in contact, it absorbs the heat to a particular amount. Then the phase changes. The heat which is associated with this phase change process, as we already learned in thermodynamics, is known as latent heat. So that is the amount of heat which a particular material absorbs at constant temperature in order to change the phase from solid to liquid or liquid to gas. Right. So that's how there are two associated two components of the heat by which they take away from the system. That's why they are included in the advanced materials which are used in the cooling technologies. In the second phase change like category on which we rely on, or which we can put certain technologies under that head, are the making changes to the physical setup, like micro channels, heat pipes, vapor chambers, immersion coolings, etc. Now, just want to mention about the immersion cooling. Now, they are they are used for a very high heat emissions components or assemblies or products which are associated with a high heat emission values. In this, what happens is you submerge the entire component or the assembly in the dielectric fluid for direct heat absorption. The more is the contact area, more is the heat absorption, right? And better the cooling technology is. Let's move on to the next slide. Here we want to talk about the latest solutions that ensures that the electronic assembly is safe from unexpected shocks. The principle remains that the shock absorbing mechanism behave like a buffer zone that absorbs the impact of the momentum before it is transferred to the main assembly, comprising vulnerable components. For example, let's understand this by the bumper in your car. Now, this bumper is designed to crumble under any type of collision, mainly head-on collision, because during the head-on collision, your bumper would be the first body that is going to come in the line of defense. Correct. Now, what happens is, as soon as the collision comes, the impact energy is absorbed by the bumper. It changes its shapes. The kinetic energy is converted. It changes, the transforms the shape, or that's what we call crumbles, before the energy is being transferred to the passenger cabin. That's how the amount of impact energy or amount of shock which is coming in is attenuated before it is transferred to the passenger cabin, making it a safer option and reducing the amount of impact which will be observed by the passengers which are sitting in the which are who are sitting inside the car. Okay. So similarly, your different shock resistant or shock absorbing methods reduce the shock before it is being transferred to the main assembly or the main component. So different shock absorbing technologies like shock resistant enclosures, vibration resistant modules, electronic detonators, suspension system, etc. They all are captured under this slide, and they safeguard the electronic components by absorbing the shock. I want to touch base upon the flexible printed circuit boards, where it's exactly same as the bumpers. As soon as the shock comes in, they change their shape to absorb the shock and that's how they safeguard the vulnerable components. Now, as the electronic products are deployed in increasingly demanding environments, from industrial automation to consumer wearables, compliance with global standards become essential to ensure reliability and safety. Now, organizations like International Electrotechnical Commission and the International Organization for Standardization, they define testing protocols and performance benchmarks for thermal endurance or mechanical shock and vibration, etc. Few of the standards I have captured in this slide. The first one is ISO 9001, which defines the process as well as products. It touch base upon both quality, like how you are going to ensure consistent quality in processes, at the same time also on the products. That's how it enhances the customer satisfaction through effective management systems. Next one is the IEC 61004, which talks about the EMC standards. The next one which I have included in this slide is IEC 60068 environmental testing. Now, This environmental testing method gives a complete detailed information about how you're going to do the shock analysis, apart from other details also. But in just to give you a gist, or just to give you an information of what are the things which it discusses. For example, IEC 60068 2 14 covers the entire thermal shock, rapid temperature change, and thermal cycling for electrical and electronic products. Similarly, IEC 60068 2 27 describes the standard process for testing mechanical shock resistance. What is the amount of shock which the product has to undergo? What is the sine wave? Even the sine wave is also defined, that this is the sine wave which the product has to undergo when it is clamped on the vibration table, right? In order to pass the test, or in order to ensure the compliance or standard. Now, as we conclude, I would like to reiterate that the key takeaways from today's session, we discussed the importance of thermal and shock analysis in electronics, which cannot be overstated. Now, these simulations are no longer optional, but essential for product reliability, user safety, and global compliance. Right. We also touch base upon different standards, which touch base upon the overall overview of how a simulation process works. We also touch base upon why, how, why, and why is it important to do, because of the going miniaturization, which is consistently, which is making the products or electronic assemblies smaller and smaller. At the same time, the features are increasing with every new model which is coming in into the market. Okay, that's how the thermal analysis becomes more and more challenging, right? And finally, with our in-house capabilities, from predictive simulations to failure analysis and compliance reporting, we are well positioned to support you in creating smarter, tougher, and more reliable electronic systems. Now, with that, we come to an end of today's session. I hope I was able to provide you insight into thermal and shock analysis in electronic products, which enhances your learning, at the same time gives you a better understanding of what exactly thermal analysis do, what exactly a shock analysis do. Now, before we end, I would like to mention areas in which we can collaborate to make better products and also elevate your design to next level. Now, services we offer apart from the thermal and shock analysis, we also offer you structural and strength analysis. We offer you fatigue analysis. We can help you to stage design for X workshops. We help you with compliance and also for creating custom reports. Now, feel free to reach out to me or Devesh. I have mentioned the email ID on the slide, and we'll be happy to hear from you anything with respect to the feedback of the session or any other topic which I have discussed in this slide. Because of the time constraint, I have not mentioned very elaborate details about a particular topic, but only touch base upon different avenues of thermal and shock analysis. If you want to know more about any topic you want to discuss with us, we'll be happy to cater you. Also, I would like to mention that a recorded version of this webinar will be available on our website in a week's time from now. We'll also send you an email with the link on your registered email ID to access this webinar. Now, thank you so much. Thank you so much for joining in, and thanks for providing your time.